Right, hello Year 11. We have got time, so we're going to look at this lesson again because I don't think everyone fully understood what was going on. The law of the conservation of momentum. We've got this equation here, F equals ma. That's Newton's second law, right? Newton's second law. If an object accelerates, its velocity must also change. Now we know momentum is mass times velocity. If that object accelerates, we get a change in momentum. It is lower at the start and higher after the object has accelerated. We are going to use F equals ma today, and we're also going to be using momentum is mass times velocity. But we can rearrange these equations. If you have a look at the page with the husky pulling the sledge, I'm just going to try and explain how we can get yet another equation to work out force. So, if F equals ma, and we know that acceleration is the change in velocity divided by the time, then what I'm going to do is I'm going to substitute this A for this here, right? So F equals m v change in divided by t. Now we know that m times v is momentum. M times v is momentum, which is given the symbol p. We've got m times v here. So the change in m times v is the change in momentum divided by the time. So the three equations that we're going to be looking at today are, once again, F equals ma, P equals m times v, and this substitution, F equals the change in momentum over time. So let's have a look at question 4a. At liftoff, we want to calculate the resultant force. That is our thrust. Take away our total weight, which gives us this value here. Don't worry about the meganewtons. Then it says calculate the acceleration. Well, if we know that F equals ma, we can rearrange that to work out what the acceleration is. It's the force divided by the mass. We've worked out the resultant force to be that divided by the mass that was given here. And there is our acceleration. Now question 5, we can read through that, but what we're after is the mass of this MMU. What we've done is we've rearranged the F equals ma equation. So we want to know what the force is. The force is 60 newtons. Divide that by the acceleration, which is 0.25 meters per second squared. That gives us the total weight of the MMU, the manned maneuvering unit. But of course, if you want that 240 is the mass of the astronaut plus the MMU. So to work out the MMU on its own, it's the total mass, take away the mass of the astronaut, gives us 160 kilos, which is the mass of the MMU. Okay, we're trying to calculate the momentum of the rocket. Momentum is given by the term P. P is m times v. The mass, 2,040,700 kilos, there it is, multiplied by the initial speed, which is 2,600 meters a second, gives us a momentum at plus 200 seconds of this value here. Now if we do the same for plus 300 seconds, it's the same mass, but it is multiplied by 4,400, so we get a larger momentum. Now B says calculate the change in momentum. The change in momentum, which is P, is the blue value, take away the green value, and we get this value here. Now, using the equation that I discussed earlier, that is F equals change in momentum divided by time. We've got the change in momentum, that's that value there, divided by the time. Now there's a time difference, obviously. It was 200 seconds and then 300 seconds, so the time difference is 100. And so we get this resultant force, because it's accelerating upwards. I've added in this little arrow here just to show the direction of the rocket. Now, question D says, during this time, the rocket is gaining altitude and losing mass. Explain how both of these affect the forces acting on the rocket. Well, gaining altitude is going to reduce air resistance because there's less air particles further up. It's also losing mass due to rocket fuel ignition, so there's less weight force. But because the thrust from the rockets is constant, it means the resultant force is going to increase. In other words, we've got our rocket here. These forces are reducing, whereas the thrust from the rocket is constant. So we're going to get an increase in the resultant force. So question 7a is talking about calculate the change in momentum. Remember, momentum is mass times velocity. We've got our mass at the start of this, and it's docking, so it's decelerating. Okay, so this is the higher value, so that's our starting momentum. Our end momentum, just before it docks, or as it docks, is it's got the same mass, but it's much less velocity. So our momentum is much less. And so our change in momentum is the big number, take away the small number, which gives us 82,225 kilogram meters per second. Okay? Now, B, calculate the resultant decelerating force. If you remember, force is change in momentum divided by the time. We've got the time here at 5 minutes, but obviously you have to turn that into seconds. So for B, we've got our change in momentum, which is this value here, divided by the time. The time is 5 minutes times 60 seconds. That is going to give us 300 seconds. That gives us our little value here. And so the resultant decelerating force is 27,408 newtons. Now, question C. The Soyuz has 3 retro rockets. You can see 1, 2, 3 retro rockets. They are firing off in this direction. But of course, the rocket is still moving in this direction here. Explain how these rockets can decelerate the Soyuz. By turning on the retro rockets, the resultant force is going to be lowered. Remember, the forces are in opposite directions, so you're going to take them away. If the mass stays the same, and the force is reduced, then the acceleration is going to be reduced as well. Year 11 triple. Not easy. But if you go over the video, pause it, rewind it, have a look at it again, then hopefully some of this will just start to sink in. Okay? See you next time.